Hello students and welcome back to CBSE Tech Talks. In today's video, we will explore an essential concept from class 11th, computer science, and that is Boolean logic and Boolean circuit. In the middle of 19th century, an English mathematician, George Boole, developed rules for manipulations of binary values, that is 0 and 1, known as Boolean algebra. This is the basis of all digital systems like computers, calculators, etc. In computing, Boolean logic means a result that can only have one of two possible values, true or false. Boolean logic takes two statements or expressions and uses a logical operator to generate a Boolean value that can be either true or false. Before moving further, let's see what are the learning outcomes of this video. By the end of this video, students will be able to define basic Boolean logic operations, that is AND, OR, and NOT, recall the symbols of standard logical gates and their truth tables, explain the working of basic logic gates and how they respond to Boolean expressions, interpret truth tables and relate them to logical gate circuits, construct truth tables for given Boolean expressions or circuits, draw simple logic circuits based on Boolean expressions, and postulates and laws of Boolean algebra. Before moving further, let's understand the terminologies which will be used throughout the video. The first one is logical statement. It is a statement which can tell only two values, that is true or false, and are called logical statements. Second one is logical constant. The truth values of logical statement are called logical constant, and truth values are true or false. Next one is truth table. It is a table which represents all the possible values of logical variables or statements along with all the possible results of the given combination of values. Logical operators. These are the operators which are used to form compound statements like and, or, not. Tautology. The compound logical statements which are always true are called tautologies. Falsy is all the compound logical statements which are always false. Logical gates. Gates are the circuits that have at least one and usually more than one input and exactly one output. Input as well as output values are logical values, that is, they are either true or false. Logical circuit. A logical circuit is a circuit that carries out a set of logical actions based on an expression. Now, what is logical operations? Now, with these two examples, we will understand the basic logical operators and or. You can go out, in example 1, it's mentioned, you can go out to play if, you can say, go out to play if it is not raining and you have finished your homework. If you see here, it is and is the you can say joining, it is a term used to join these two conditions, not raining and have finished the homework. Now the output of this expression, or you can say you can go out to play, will be possible only when this condition and this condition are true. Now if we go with both conditions must be true, no rain and homework done. If either one is false, you can't go out. So the possible combinations is not raining, finish homework, not raining, not done homework, raining, done homework, raining and not done homework. So as it is and, so true will output will be true only in the case when both the conditions are true. For rest all cases output is false. So this is how we go with and. The output of and operator will be true only when both the conditions are true. Example 2, you will get a reward. So this is the output if you score above 19 math or win the science fair. Now or is mentioned here, it means either this condition or this condition, and even in the case when both the conditions are true, you will be rewarded. So even if only one condition is true, you get the reward. So conditions are score above 90, win science fair. Score above 90, not science fair is not won. Score not above 90, but the fair is won. Neither score above 90 nor the fair is won. So only in this case the output is false. For rest all cases output is true. So this is how we go with and OR logical operator. Now let's see the example how we make a truth table. Now in this case we have expression given here is x, y and z. There are three inputs, three variables are there. So the possible combination, input combination will be 2 by 3, 2 to the raised power 3, that is 8. So we have these 1, 2, 3, 4, 5, 6, 7, 8. Now these are the 8 combination, but how to make combinations? The very easiest way is write all the 3 inputs at the top and the extreme right change in alternate. So if you see, this is a pair of 2, 0, 1, 0, 1 and 0, 1. Now the second input is 2 zeros, 2 ones, 2 zeros and 2 ones, and the third one is 4 zeros and 4 ones. So in this case, if you write this way, you will not forget you will not forget any of the possible inputs. Now first off, before finding out yz complement, you need to find out yz. So what is y and z? So output of y and z will be true when both the inputs will be true. So there are only two cases, this one and the last one, where both the inputs are true. So for this and this we have output 1, and for rest all cases we have output 0. I think 0 0 is 0, 0 1 is 0, 1 0 is 0, 0 0 is again 0, 0 1 is 0 and 1 0 is 0, and for 1 1 and 1 1 output is 1. Now as we got yz, now we are finding out yz complement. So whatever is yz complement will be inverse of that, or you can say reverse of that. So 0, so 1. It is again 0, so again 1. 0, 1, 1, 0, 0, 1, 0, 1, 0, 1, 1, 0. I think this is clear. And the last term is x plus. So this is we already got, and x is here. So what we will do, we will have OR operator between these two. So in these two cases, take these two values and output will be 1 where we have any of the input as 1. So in this case we have 1 here, here again 1, here again 1. Then in this case, this is the case when both are 0. This is the case when both are 0. So only this is the case when both are zeros, we are getting output as 0. For rest all cases we are getting all 1s. So this is how we make truth table. Let's move to the gates. So there are 3 basic gates, that is NOT, and OR. NOT is what? Inverse of you can say input. So when input is 0, output is 1. When input is 1, output is 0. I think this is very much clear. This is the only gate which is having 1 input. Rest all gates have minimum 2 inputs. This symbol is for AND gate. When we talk about AND gate we have done in the previous example. When A is 1 and B is 1, then only the output X will be 1. For rest all cases it will be 0. So this is symbol for AND. Now the possible inputs are, again I'm repeating, 0 0 0 1 1 0 and 1 1. So this is AND. We write this A and B, or you may write A dot B. So in our first 3 cases both the inputs are not high, or both the inputs are not true, so that's why output is false. While in the last case both the inputs are true, so output is 1. The next symbol is for OR gate. This is for OR gate. Now in the OR case, output will be true when any of the input is true. So except first case, all the cases are true because either of the input is true or both the inputs are true. So these are the truth table. You can say truth table for NOT gate, and this is truth table for AND gate. Eliminate this column, then it will become truth table for AND. Now these are few more gates, that is NAND, NOR, exclusive OR, exclusive NOR. NAND and NOR are known as universal gates. Using these two gates you can draw any circuit. This was the part of syllabus till 2-3 years back, when the conversion of all the gates using NAND and NOR was the part in the syllabus, but now it is not there. If any student want this extension or this extra, please comment me. I will make one more video advance of, you can say, logical gates and Boolean algebra. Otherwise, I'm not including in that. Now, what is NAND? NAND is not and not, means the complement of and. So this is, if you remember, in the last slide I showed you that this is AND gate and this not, this is the symbol for not. So this is NAND, okay, and output of NAND will be inverse of AND. So and not, this is or, you know, and this is this circle is extra, or this is for not. So this is nor, or and not. So what we can, and these are, this is or is there, and exclusive or. This is exclusive nor. Let's go one by one. We know that there are, you can say, two inputs, so there will be four possible combinations. So A dot B, this is what? AND. So AND will be true only when all the inputs will be true. For rest all cases it will be false. And this is not of AND, that is NAND. So we took the inputs of and we are complementing. So 0, 1. So this is again 0, the complement will be 1. 0, complement will be 1. 1, complement will be 0. Now this symbol is for OR gate. So A or B will be true when any of the input is true. So other than first, all the cases are true. And this is NOR. What is NOR? A complement of or you can say not of or. So we will be complementing or inversing all the inputs of which is A plus B. So other than first, all are zeros. This symbol is for exclusive OR. In the case of exclusive OR, what happened? The output will be true when inputs are not same. The real life example of this is the switch, or you can bulb or tube light in your staircases. So we have one switch in the, you can say, on the ground floor, and one maybe on the terrace. If you have, you can say, only one floor building. Otherwise you have two switches in all the floors. One is for the lower switch and one is for the up, that's only. So when any of the input is true, or when inputs are not same, you can say, otherwise the output is 1. So this case is 0 and 0, so output is false, and this is 1 and 1, output is false. In this case, inputs are not true. So one is 0, 1 and the other one is 1, 0, so output is true. So this is for exclusive OR. This is for exclusive NOR. Output will be true when inputs are same. Okay. So for these two cases, output is 1. For rest all cases, output is 0. I think it's clear. Let's move to the next slide. Now there are some basic postulates of Boolean logic. Okay. Now if we see, if x is not 0, then the value of x will be 1, because x can have only two values, 0 and 1. If it is not 0, definitely it has to be 1. And if x is not 1, then it will be 0. I think this is clear. When we talk about logical AND addition, 0 plus 0 is 0, 0 plus 1 is 1, and 1 plus 0 is 1, and 1 plus 1 is 1. This is OR gate. We just now did in the previous slides the truth table of OR, and even we took the logical condition also, like you will be rewarded if you score above 90 or you have won the science fair. That's what we can go with. Logical multiplication, or you can say AND. Output of AND will be true when both the inputs are 1. For rest all cases, if it is 0 and 0, output is 0. 0 and 1, output is 0. 1 and 0, output is 0. 1 and 1, output is 1. And the last one is complementary rule. If input is 0, the complement of 0 is 1. If input is 1, complement of 1 is 0. So these are the basic postulates of Boolean algebra. Principles of duality. Now what is principle of duality? Every Boolean expression has a dual expression. If the expression is true, its dual will also be true, and vice versa. It means if expression is true, the duality will be also true, and if expression is false, duality will also be false. Now what is the process to convert the expression into dual expression? So you have to change each OR sign to an AND sign. It means convert all the pluses to dot and change all the AND signs to OR. It means you have to change OR to AND 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 to OR. The last one is replace each 0 by 1 and each 1 by 0. So this is the rule for duality. Okay, if we have to find out duality of this, what will be expression? A dot B plus C dot 1. Now 0 and D is bracket, so it is again 1, so sorry, and so it will become or D dot 0. Am I clear better? So we have done what? And is made to or. So there are how many ors? 1, 2, 3 ors are there. So we have 3 ands, 1, 2 and 3. And there were and gate here, there were and here, and there was at two places there were and, so we have got 2 as ors. And there was 0, so 0 is converted to 1 and 1 is converted to 0. Let's do one more to make you more clear. Now A dot B. Here there is and, so let's put or. A complement dot B complement equals to, here it is and, so let's make it or A plus B dot A plus C complement. I hope this is clear now. Let's move to the next slide. Now these are some of the basic theorems of Boolean algebra. Now there are many theorems which you have already done in mathematics, so we will not go in detail for those, but which are not in mathematics or which you somewhere you feel like how it has delivered or how it has you can say come, I will be showing you using truth table. The first one is property of 0. 0 plus x is always x. It means if the value of x is, let me try here, if the value of x is I'm taking with this one, so 0 plus x, when the value of x is 0 or value of x is 1, so output will be 0 plus 0 will be 0 and 0 plus 1 will be 1, and this is same as the value of x. So 0 plus x is x, same goes with 0 dot x. So whatever value of x will be there, as there is 1 0 and we are going with AND operator, so anyhow the answer will be 0 only. It can't be 1 because for 1 both the input need to be 1. Now in this case, if you are doing 1 plus x, whatever may be the value of x, as 1 is there and we are going with OR operator, so you will be getting output as 1. In this case, when 1 dot x, so for dot means AND. So for AND, you should have both the inputs as 1, then only you will have x. So depending upon the value of x, you can say this way. If it is 0, so 1 dot 0 is, or 1 dot OR is 0, and 1 and 1 is 1. So it is going with the value of x. Now the second one, this is property of 0, property of 1, in Dupuytren's law. In this case, you may have n number of values of same type, output will be that one value only. So x plus x plus x is, you may write any x's, it will be x only. Same goes with for the, you can say, AND operator also. So x and x, it will be going to give me x. Now evolution law is what? Complement to complement is number itself. Let's take an example. If we have this thing, so complement of 0 will be 1 and the complement of 1 will be 0. Go the other way. Complement of 1 will be 0 and complement of 0 will be 1. So it is coming to the same one. If it is x, it is going to give you x only. Complementary law. X plus x complement will be 1. Because if it is x, it will be 0. If it is 1, it will be 0. So 1 plus 0 is 1. If it is 0, it will be 1. So 0 plus 1 will be 1. But here, the complement, when we are going with the AND gate or AND operator, the complement and the number will be 0, because in each and every case, one of the input will be 0. So output will also be 0. Commutative law, either you do x and y or do y and x, you are going to get same answer. Same is the case if you are doing x and y or y and x, you are going to get the same answer. So these are also clear. Now let's come to the associative law. Now if you are adding these two first, or you are doing OR of these first, either OR of these two or OR of these two, and doing the third element as an OR, you are going to get same answer. Let's do using truth table. So there are three inputs, x, y and z. So there will be 8 combinations: 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. I told you in the previous slide. So this, the value of x will be changing after 4 inputs, the value of y will be changing after 2, and the value of z will be changing alternately. Now when we go with y plus z, or you can say x or z, output will be 1 when any of the input is 1. So in this case this is 1, here it is 1, here it is 1, both are 1, here it is 1, here it is 1, and here it is 1. So only for these two cases it will be 0, for rest all cases it is going to be 1. Now we got y plus z, we have done. Now add x plus, this is already done, this is already done. Now add this to x. So x is this and this. If you go with 0 plus 0, 0, 0 and 1, 1, 1, 0 and 1, again 1, 0 and 1, again 1, 1 and 0, again 1. So other than first case, all other cases are ones. Now let's take first do the OR between x and y. So this is, first one is 0, second one is 0, third one is 1, fourth one is 1, fifth is again 1, sixth is again 1, seventh is again 1, eighth is again 1. Now we have got, already we have done x plus y. Now this plus z, so z is this one. So 0 plus 0 is 0, 0 plus 1 is 1. So you are getting then again 0 plus 1, 1, 1 plus 1 is again, of course 1, 0 plus 1 is 1, 1 plus 1 is 1, 0 plus 1 is 1, and the last one is also 1. So if you see, these two are same. So this first one is explained. Let's do the second one. I will be doing second one for you. Y or y and z. So when both inputs are true, then only output will be true. So for this case we have, this is the fourth case, and eighth case we have 1, rest all cases we have 0. Now we got, already we have y and z. Let's do x with this. So if you will do this x and this yz, so we have to see only the case where this output is 1, this is 1, but here it is 0, so it is going to give you 0. Only in the last case both the inputs are 1, so we have 1 only here. Let's do x and y. So x and y, first case is 0, second is 0, third is 0, fourth is 0, fifth is 0, sixth is 0, seventh and eighth are 1. So I mentioned here 1. Now the last one is x and y is done. Let's do and of this with z. So first one is 0, both, second one is here 1 but here 0. The third one is here 0, both are zeros. Here 1 but here it is 0. Fifth one here 0, both, even here 0. Sixth one is 1 here but here it is 0. Seventh one here 0 but here it is 1. Only in the last case both are 1, so this is true. So if you see here, this equals to this. So we have proved using truth table. So this is what, either you add these two, or you add means here or you and these two, you are going to get same answer. Let's move to the next theorems, few of the theorems. Distributive law is, if we write x, you have done this in the simplification of equations in maths classes somewhere in 7th and 8th. So if we have x dot y plus z, so we open the brackets and we get x dot y plus x dot z. Same goes here. Now when we go with x plus y dot z, so in this case as plus, see, whatever is going applicable with OR gate is also applicable with AND gate. So we have x plus y dot z. So it will be x plus y, and this symbol here it was plus, so it was plus here. Now here it is dot, so dot is coming here. So x dot y plus z equals to x and y plus x and z. If you have x or y and z, you will be having x plus y and x plus z. And the third distributive law, which is not there. So if we have x plus x complement y, it will be x plus y only. Let's do these using the truth table. It will be more clear. So combinations are already clear to you, that which all combinations will be there. Y and z. Y and z, as we have 0, 0, so 0, 0, 1, 1 is coming. We are going with OR. So in this case 1 is input 1. Here also 1 input. Here both are 1. Again here it is 0. So other than first and you can say fifth, rest all are 1. Now when you are doing AND of this we got y or z. Now make AND of this. So this is 0, here it is 0. We have to see only when it is 1, we have to check for the other input as 1 or not. So this is 0, it will going to give you 0. Here it is 1, but here we have 0. It is 1, but here we have 0. Again 1, here we have 0. Now here we have 0, we can ignore what is there because 1 has 0 come means it can't be 1. Now here it is 1, even here it is 1, so 1. Here 1 and 1, so again 1. Here also both are 1, so output is again 1. So this is last three are 1, rest all are zeros. X and Y. X and Y first, second case will be 0, third case the value of X is 0, fourth case will again the value of X 0. So for first fourth, straight away you can write 0. Here the value of Y is 0, so again fifth and sixth is again 0. Last two are true because it is 1 1 and 1 1, so it is mentioned here. Now X and Z. So for first four cases the value of X is 0, so anyhow the X and Z will be 0. For the fifth case, the value of Z is 0, so again 0. Sixth case, both are 1. This X is also 1 and Z is also 1, so we have got 1 here. Seventh case, the value of Z is 0, so we got 0. And for eighth case, both are 1, so we got 1. And when we are adding these two, and when, or you can say when we are doing OR of this, 0, 0, 0, 0, 0, here it is 1, 1 and 1. And see, if you see here, this as well as this is same. See the output. It means the expression this is true. We assume that this is true because we have got using the truth table right answer. Let's do the second one. Y dot x z. So we need here y dot z. So y dot z will be true. This can't be true. This can't be true. This is true. So this is one case where it is true, and this is the last case where it is true. For rest all cases it is false. Now make this and x. So if any of the input is 0, if any of the input is 1, output will be 1. So for first three cases, this is 0 and even x is 0, so 0. For the fourth case, x is 0 but y dot z is 1, so 1. For fifth, sixth, as x is 1, so you may ignore this, all are 1. So last five cases are 1. X plus y beta, if any of the input is 1, output will be 1. So for the first case both are 0, second case both are 0, third case 1 is 1, so it is 1. Fourth case it is 1, so again it is 1. Fifth case, this the value of x is 1, so it is coming 1. For this case the value of x is 1. Again for last four cases the value of x is 1, so it is coming 1. And for the first two cases, you can say these two cases, for these cases x was 0 but the value of y was 1, so it is coming. So first two are zeros, rest all are ones. When you go with x plus z, x and z, so it is 0, the second one is 1, again 0, 1, again 1, 1, 1, 1. So other than first and third, rest all are zeros. Sorry, other than first and third, others are 1. Now you can say AND of between these two. So output will be true when both the inputs are true. So this is 0, obviously 0. This is 1, let's check the other one, 0. This is 0, it will 0 only. For these all cases it is again 1. So if you see here, this and these two are same. So even this, you can say this theorem is proved. So we have to accept that if we have proved this, means it is very much clear that it is going the same way. Let's do the distributive law, explanation of distributive law in the next slide. Third distributive law. So it is x plus x complement y, it gives you x plus y. So as there are only two inputs x and y, so we will have only four combinations, 0 0 0 1 1 0 and 1 1. X complement will be inverse of x, so first two are zeros and last two are 1, so it will be first two ones and last two zeros. X complement y, this is 0, both are 1 in this case, so output is 1, and here it is 0 and 0, so only one case will be 1. Now let's do x plus x complement y. So the x complement y is already done, add this to x, so 0, here it is 1, so other than first, rest all are zeros. And we know x plus y is what? OR gate. OR gate is only false in the first case when both the inputs are 0, rest all are true. So this is proved. This, you can say, this has come equals to this thing. We will be using these to solve the calculation or to prove something. So we can straight away write this. There we don't have to simplify or we don't have to do it. We can straight away replace one side, left hand side, with the right hand side. The last one is absorption law. In this case, if we have x plus xy, answer will be x. So y is absorbed here. If we have x dot x plus y, again x, y is absorbed here. Let's do. using truth table. So there are four possible combinations: 0 0 0 1 1 0 and 1 1. So xy will be true only when both the inputs are 1. That is the last case. And if we have OR of xy, it will be first two cases will be 0, last two cases will be 1. X plus y, we know that output will be 0 only in first case, rest all cases are ones. And x dot x plus y will be this and this. So first one is both in the both the cases, first one is 0, so 0. Second case, x plus y is 1. So as we are having AND gate here, so it will be true only when both are true. So this is one we have to check for x is 0, so again 0. Last two cases both are 1, so we have 1. So if you see this column and this column, all the outputs are same, so even this law is proved. So we assume this law also. So you have to remember these laws to simplify the next you can say conversions, or you can say proofs. This is De Morgan's theorem. In this case, what happens? X plus y bar equals to x complement dot y complement. X and y complement equals to x complement plus or complement. Okay, so what we are doing? We are complementing all the inputs and we are converting, you can say, OR to AND 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 to OR. Okay, let's do algebraically, you can do easily. Let's do using mathematical. So we will start with it. So I will be explaining you this theorem. So we have x plus y complement equals to x complement dot y complement. To prove this theorem, we need to recall the complementary law. What is complementary law? We know that x plus x bar equals to 1 and x dot x bar equals to 0. If we prove these two equations, using this we will assume that this equation is true. So now to prove De Morgan's first theorem, we will use complementary. How you are going to go? If x plus y complement equals to x bar dot y bar, then we can write x plus y plus x complement y equals to 1. Am I clear? We have used this as it is and we took the complement. We know x plus x complement equals to 1. So this is, we are assuming that this is x, so this will also be x because left hand side equals to right hand side. So we took the complement of this number and we took as it is, and we know that x plus x complement is 1, so we are writing this way. And the second will be what? X plus y dot x complement y complement equals to 0. If we prove this equation and this equation, you will assume that this equation is true. Okay. Now what we will do from this, x plus, I am writing once again. Now what we can do, we will be following this one, this theorem. What is it? X plus y dot z. Yes or no? If we have this x plus yz, so we have x plus y and x plus z. Let's assume this as x. So what will happen? X plus y plus this x bar, x plus y plus y bar. Okay, and we know x plus x bar is what? 1. So from this and this it is 1 plus y. These two are making 1, so x plus 1. And we know that 1 plus x is always 1. 1 plus x is always 1. So what is it? This will become 1 plus 1. And this is again become, this all together will become 1. And this is also 1. So 1 dot 1 is what? 1. Am I clear? Should I explain once again? Let me explain once again. I am taking it. Okay. So now what I have done, we know that this is x and this is the other one. Okay, we will be proving this as 1 and we will be proving the next one as 0. So what we have done, we know that this is the equation we have already proved, which is this rule or regulation. You can write straight away this. If you are not able to recall the name of postulate, you can write x plus yz is x plus x dot x plus z. So we are assuming this as one term and this as x complement and y complement. So what will happen? X plus y, so this will be taken x bar and x plus y bar. We know that x plus x bar is what? 1. So 1 plus y, here it is y plus y bar. So y plus y bar is what? 1. So x plus 1. We know that 1 plus any input, 1 plus y will be 1, and you can say 1 plus x will be x. So this is, both are x. So we are getting the answer as 1. Let's take the second one. Should I prove this here somewhere? I am proving it here. So what is this equation? X plus y, x bar, y bar equals to 0. This is only to be proved, isn't it? So how to go with? How to write this thing? We all know that we will be using x, y plus z equals to what? Xy plus xz, yes or no? Is this not done in the previous classes? So what we will do, we are doing x plus this and then again we are multiplying. So what we will do this time, we will take this as an input. So y bar, z bar, x plus x bar, y bar, y. And in this case, what we will take? X dot x bar is what? 0. So this will become x bar and y, x will become 0. 0 dot y bar plus x bar. This will become 0. And we know that 0 dot anything is what? 0. So it will be 0 plus 0. And we know that 0 plus 0 is what? 0. So this is proof. This is proof. I think you are clear now with that. If both the, you can say we have proved both the postulates, then it means that the equation is right. Second equation I'm leaving up to you to solve on your own. If you are not able to do, let me know. I will even explain that also in my next, you can say in the video where I will be taking the exclusive or also. Complement of Boolean expression. Now the next one is how to get the complement of Boolean expression. Now what we will do, complement the entire function. First of all, you put complement of the complete function, change all the ends to or and all the ors to and then complement each of the individual variable. So we have to change the gates and we have to complement the variable also. Let's take a question, one example here. If we have A plus BC, okay, bar, we have to find out complement of this. So first of all, what we will do, A plus BC bar, and we will be putting complement of complete. So first part is done, complement of entire. Now the next thing will be done is that we will be using De Morgan's theorem. What is De Morgan's theorem? A plus B equals to A bar dot B bar. So we have this as one term and this as other term. So we will be getting as A bar dot BC. This is already bar and bar to bar. And we know that complement to complement is itself. So it is A bar dot BC. So isn't we follow the same thing? We took the complement, we have changed and to or and or to and we have put all the complements. So A was simple A, so A complement, plus has become dot, and then this was is B and C both were having bars, so both are removed. So this is the way to find out the complement of any expression. We can go with any other expression also, A plus B dot, you can say plus AB, you can say. So let's, if this is the case, if this is the equation and we have to find out complement of this, we will put complement here. Now we will assume this as one term and this as one term. Let's follow the De Morgan's theorem. What is De Morgan's theorem? A plus B bar is what? A bar dot B bar. So what will happen here? AB, so A plus B bar dot AB bar bar. Now A plus B, again follow the De Morgan's theorem. So it will become A complement dot B complement dot complement to complement is this thing. And if you go straight away, this is the, I can say, complement of this. If you go straight away with this, what we are doing, we are putting the complement, plus will become dot. We are again putting the complement, plus will become dot. Again we are putting complement. This was bar, so bar will be removed. So this is what I have derived from this. I think this is clear to you now. Should we move further? Now, how to draw the circuits, logical circuits. Rules to create logical circuit are: break the Boolean expression into sub-expressions. Let's take an example here. If I have Boolean expression as, you can say, AB plus B complement C plus AC. If this is the circuit I need to draw, we will be following the instruction. Break down the, you can say, Boolean expression into sub-expression. So this is one sub-expression, this is second sub-expression, and this is third sub-expression. Determine the logical gates that can implement each sub-expression. Here it is what? AND. Here it is what? Again AND. Here it is what? Again AND. So we are having AND in between that. Implement sub-expression using gates. So what will happen? We will be using A, B, and this is having AND gates. So AND gate symbol is, so we can write here it is AB. Then we have B bar. So B bar is not of B. So what we will do? We will be taking, this is B and this will become B bar. And the next one is C. This is C. So again this is AND gate. So this is what? B bar C. And the third one is A and C. Again it is also having AND gate. So A and C. So we have done till here. Implement the sub expressions using gate. Determine the logical gate for the symbol using the sub expression. Okay. Determine the logical gate for the symbols joining the sub expression. So this is, what is the sub expression? How they are joined? So here it is OR. And here it is also OR. So there is OR gate used in it. Using the logical gate for the joining symbol, connect the sub expressions into implementing. So there are three inputs now. We have three inputs. We can move this to one, and this is our OR gate. So we will be writing AB plus B bar C plus AC. Now we have took 6 inputs, 1, 2, 3, 4, 5, 6. Basically we will have only A, B and C. So exactly how we have to go with, this has to be connected here, this has to be connected here, and you can say you have connected it here, and C is connected here. Now this C we will be using drop down to connect here, and we will be using drop down to connect here. This also means you have to leave it here, and then we will be connecting here. Am I clear? So inputs are basically 3 only, and we are going to go with. Let's do one more circuit. I think this need to be, one more need to be used. Okay. Any expression you can have, you can say, let me use it. Cut only for, I will be using this as a blank, and I will show you. Okay. So if I have any expression, let's take an example, A dot C complement plus BC plus, you can say, A complement B. Now we have 3 inputs, beta. First of all, we will be taking, this is A, this will be using B, and this will be using C. Okay, now this subpart A, C complement. So what we will do, I will take one, you can say, I will take a one, I will draw here, and this is what. So I will be drawing here, and we have C complement, so it means not of C. So this is C here, it has become C bar. Now we will be joining it. This is having AND gate. So we know the AND gate is symbol is sort of D here. So this is A, C complement. The next one is B and C. So B, and you can say we are making this way, C. So this is BC. Third one is A complement B. So I need to bring A, and then I need to take the complement of A. So this is A complement. Then it is B. So B need to be brought here. So this is B. So this is again having OR gate. So it is A complement B. Now in between all these three, we did the you can say divisions. In between these all we have OR gate. So we can have one OR gate, bigger OR gate also. So this is having this input as well as this input. So you can go with this, you can go with the diagram. So this is the output, which is A, C complement plus BC plus A complement B. I think it's clear now. Now, thank you for watching this video. Please do like, share and subscribe to this channel so that I can put other videos, and the moment I will put you, it will be received to you, or it will reach to you, and you will be benefited from this. If you have something, please do write in the comment so that I can make more videos on that. Okay, see you in the next video.